finally, finally, I've open sourced my implementation of the original transformer paper. Attention is all you need, and it took me like 3 weeks of nonstop working on this, and I'm super happy. I learned a lot, and hopefully you'll find it as a valuable resource as well. So yeah, let me just walk you through this README. This is the architecture. I have some nice visualizations here, and I have two models which I've pre-trained, which I've linked. So yeah, before I get into this, the code itself, I just want to tell you about a couple of things, like the whole journey I had learning about this. And so those of you who've been following me over the last a couple of weeks, you know that I've been working on transformers for more than a month now, and I first started by just reading about theory, reading like research papers for more than like two plus weeks. And then after I finished that one, I basically started coding the implementation from scratch, and that took me around 3 weeks, more or less. So let me start with why I did it. So the thing is, I looked for like good resources to understand transformers, but not on the level of theory, but to be able to actually understand the code itself. And I basically only found 2 decent resources, good resources. And I'm not counting in Hugging Face, because they do have a really awesome library of transformers, but they are more for as a black box experience type of usage, and not for going through the code and understanding how stuff works. So the 2 resources I mentioned are the Annotated Transformer is the first one, and then PyTorch official implementation. Now the thing with PyTorch official implementation is that their multi-headed attention module is awesome, functionality wise it works, but the thing is it's so generic because they gotta cover a bunch of use cases. And so it's so complicated to actually go through the code and understand how it works. So my idea was to just focus on this specific use case, of this transformer model from 2017, and that's it. On the other hand, the Annotated Transformer blog is basically suited only for researchers, and also had a couple of bugs. It's a overall really nice resource, and it helped me a lot. But it's really only for researchers, and they also suppose you understand the source code of TorchText, which is PyTorch's module for manipulating NLP tasks, which is usually not the case, right? So I want to make a couple of points before we go and take an overview of the code, and I explain you how I struggled, which problems I had, how I approached it. I won't get into every single detail because the code base is now already pretty big. I'll show you some details, but before that, I want to tell you that making good projects takes time. So I had a couple of comments. I had Rahul commenting, thanks for telling us that understanding and coding a new AI algorithm takes a few months. I always felt like people are going too fast and doing things in just days, and I cannot keep up. But thank you, it gives me motivation. So thank you, Rahul. The thing is, I mean, it's funny. My first attempt at trying to reconstruct a research paper took 3 months. So I was coding 3 months nonstop. And the reason being, the authors did not open source their implementation, and you couldn't find, the code wasn't as popular as the transformer, so I couldn't find snippets of code anywhere. So what I ended up doing is just trying and reconstructing the paper by just reading text, which is super hard and it takes time. And I had lots of back and forth with the authors to understand certain vague details, and it's just. So the point I want to make here is, don't fall for that learn huge topic X in 5 days. I mean, that doesn't work like that. And I'm just wondering, I think I know why that's the case. You have Siraj Raval, who had videos like learn TensorFlow in 5 minutes. And I mean, I want to tell you something. I mean, if you believe that crap, you're in a really bad position. Because that's going to set you up for failure. And why? Because it's basically setting you up for impatience, Whereas you really truly need patience in order to create anything great. Like every single project, like the projects I'm doing at Microsoft, that's like a multi team effort that lasts at least 6 months, 1 year, 2 years, 3 years. So anything significant takes time. In artificial intelligence, in computer science, whatever the topic it is. Like I've skipped creating a video last weekend, because I was so in a flow of coding this Transformers thing up that I didn't want to break my flow and create a video. So that's how things function. You got to make trade-offs sometimes. And when we are at this point of talking about time management, let me walk you through how my commit history looked like, and how I organized my time during this 3 weeks. Okay, so let me walk you through my schedule, because I mean everybody's I've noticed a lot of comments, people thinking everybody is so much faster than they are, and that's so not true. It just takes so much time. And let me walk you through my commit history. If I open this up, and let me find some representative day like November 5th. And okay, so let's start. Like I usually start my day around 9:20, 9:30 a.m. And so I code until maybe 11:15. So usually around 2 hours every morning. And then what I do, I take a short break and like take a stroll, get something to eat, and I start working at Microsoft, where I also work full time. So it's a really tight schedule. And after I finish my daily work at Microsoft, so the good thing about Microsoft, and that's really awesome, is that it's a truly like a meritocracy system. So my managers, he doesn't care if I'm like working 10 hours or 6 hours. He cares that I get my done, and that's super rewarding. I'll get fired because of this video. No, I'm joking. So basically, I do work around 8 hours, but the good thing is they value what you do and how productive you are, and how much you sit down in that chair. Doesn't matter. You get done, and that's it. So after I finish my daily work, I usually take a power nap, and depending how tired I am, I maybe I take some more time to like rest, and then usually around like 9 p.m. like 8:30 whatever. I get working. I get to coding again, and so I work until maybe 11 p.m. 11:30. So that's again like 2-3 hours of quality coding. So that thing accumulates. So that's like 4 or 5 hours every single workday. And then I have weekends where I'm even more productive because I don't have to work at Microsoft on weekends. And at the end of the day, during work days, I usually take some time to chill. I either watch like South Park to just get just relax my brain, or recently over the last week, I've been just watching Lex Friedman's podcast, and there is just so many interesting people there, and it just kind of also relax me, even though I'm learning by watching that podcast as well. So that's cool. And now, if somebody told me even 2 years ago, about this schedule, I would tell that person you're like nuts. And the thing is, depending on your mindset and where your phase of life and your situation, this may not sound feasible, but that's what I thought 2 years ago, and then things change, and it's totally fine. So don't feel any pressure for not working as hard as somebody else, because everybody's got their own pace, and that's super fine. It took me 12 years to get in a to acquire working habits that I have right now. And initially I was just learning different stuff on my own and structuring my journeys, but they were not related to programming whatsoever. So I was learning about human languages. I'm really passionate. That was one of my main hobbies when I was in high school and beginning of my faculty. I was training a bunch of sports. I tried so many sports out there, so I was just exploring, and only at 19 did I get exposed to programming. And that's totally fine. You can still achieve things even when you start a bit later. When you're 19, that's super totally fine. One more thing, and I know it's kind of cliche, but life's not fair. So Bill Gates back in the 60s had a computer when he was 12 or 13, and I mean he started programming when he was 12, and it's still, I'll tell you something, it still doesn't matter. You can start when you're 19, 20, 25, 30, and it's still not late. If you keep up the good work and you keep like being consistent at whatever you do, you'll get better and you'll get where you want to be, and that's it. I mean, chillax. And lastly, there is one more thing I want to mention, and that's failures. And like, turn your head around you and look at successful people around you, and they all had failures. And if they're honest enough, they'll tell you about those. If they're not, well. So I linked this guy, like he's a Stanford PhD, and he was open enough and honest enough to share his journey. And that's how pretty much everybody's journey looks like. You get lots of failures. In his case, that's like paper rejections. But then you have a couple of successes, and everybody knows you for your successes, and that's it. And like me personally, I had like a bunch of failures. Like I was rejected by Facebook, I was rejected by Nvidia, I was rejected by Microsoft, and then on my second attempt, I got like accepted into Microsoft. But even if it was like third attempt or fourth attempt, it doesn't matter. Like as long as you like keep learning and you keep applying, you're set up for success. If you're just applying, then you're just spamming people. Like you gotta keep on learning and applying, and wherever you wanna be, you'll get there. Like sometimes when you get rejected, it doesn't have to be that you were bad. Like I don't know, like hiring pipelines are in big companies, in big tech companies, are not perfect. They're far from perfect. Enough about motivational speaking. Hopefully, I just wanted to share my personal story and some of details. I think many YouTube videos out there are doing similar things. There's already so much high quality educational resources, and there is too little personal stories that I felt like sharing some of the details from my life and from my workflow. And I hope you found this helpful. If you did, please leave a comment in this comment section, because I'll start creating more of these if you found it useful. Okay, all of that being said, let me kind of explain you how I think about approaching a new problem and new project. So a good thing about Transformer project, and in general about many software projects, is that they can be modularized. And what I mean by that is you can basically orthogonally, i.e. independently develop certain components and not care about others. So this project was pretty much split into two parts. So the first one takes care of training the model. And then you have the second part where once you've trained the model, you want to do translations, and you want to do some decoding on those models. So once you split like the functionalities like that, you can focus on pretty much basically only on the training side. And I had only 3 files, let's say 3 files, 3 main files, which I had to develop in order to get like the transformer model trained. And the first one is obviously like the transformer model PI file, which contains the architecture, the definition of the model itself. And so the good thing is, when I said it's orthogonal, so you can basically, I basically just developed this model, and then I created a small main function inside of this Python file where I could test whether the model is working or not before I move ahead and develop the other parts of the project. So it's never linear like that. You usually jump a little bit here, a little bit there. But let's say I basically first developed this model, and then I went and did the other things. So I figured out some bugs doing this, which is a good thing. Better catch them sooner than later, and I'll get into problems a bit later. Now let me just give you an overview of the project. So the second important thing is like data, and you want to load the data. You want to load, like in this case, so the transformer model, I should have mentioned that, is trained for the machine translation task. So basically you want to translate from one language, which is called the source language, into another language, which is called the target language. And the languages I used were English and German, or German to English, vice versa. So I had lots of problems with loading data in PyTorch. First of all, because I'm used to computer vision projects, and this was natural language processing, so it was kind of a little bit of paradigm shift. And second of all, it's nowhere as near as good as storage vision is for computer vision. So I stumbled across two significant problems. First one was like functionality wise. So the thing didn't work as I expected to do, like something called bucket iterators, which were supposed to batch the data in an optimal way, weren't working as I was expecting them to. And the second problem is the performance problem. So the tokenization procedure and everything took a lot of time. Like every time I wanted to run the training loop, it took like 45 seconds, and that's so annoying. And I think I went from 66 seconds to like 2.5 seconds, which was a massive optimization jump, and that helped me iterate much faster. And that's super important in deep learning and machine learning in general. Like you want to have a really short iteration cycle that helps you build stuff better and faster. So I'll tell you about some of the problems I had developing the data pipeline. But first, as I mentioned, let me just quickly go through other files. So then we have like the training loop, and basically the training loop is pretty simple once you take a look how. So let me show you. So basically, yeah, I prepare the model, I prepare the data. Then what I do is I just prepare some things like for label smoothing. I won't get into details what that is, like optimizers, and then the loop is really simple. So for a number of epochs, I use 20 because just looking at the attention is all you need paper and calculating stuff, you can see they approximately had 19 epochs on the WMT14 dataset. So that's what I did also, and I didn't get into any saturation regions until 20 epochs, so it was totally fine. And so the iteration loop, so I basically just have, so I do the training loop and then I do the validation loop, because you want to see how the model is generalizing to data that it hasn't seen during the training. So training loop is so I'm already getting into too much details. So you basically, once I set a training loop, I can run the whole thing, I can test it, and then what I did is I quickly made a translation script which would test whether the model was doing what it's supposed to be doing, and that's like translating from language to language. And that's super important. Like you want to have like end-to-end system as soon as possible, and then you can keep on iterating and improving either the model or the data loading, and that's how I did it. So I first had the whole thing working end to end, and only then I did those optimizations, etc. I also had to develop decoding algorithms. So what I did is I developed a simple one that's called like greedy decoding, where basically, so once you get the output distribution for the next token, you basically figure out where the highest probability is, and that position corresponds to a certain token in your vocabulary. So basically, you find the next token in your output or target sentence in that way. And greedy is the simplest method. What they used in the paper was actually something called beam search, where you keep like a number of hypotheses running in parallel, and you at the end you're left with the hypothesis that's like most probable, and you keep that one and you output that one as the output sentence. Finally, I also have something called playground file, and I do that not only because I'm open sourcing this and treating this like as a learning resource for others, but it's also a really good thing for me because it helped me understand something a lot better, and because it's much easier. I'm a highly visual person, so I like to visualize stuff. So, for example, there is this thing called, if you're familiar with the transformer model, they have something called positional encodings, which you basically add to tokens embedding vectors. And so the formula is kind of complicated, and then once you visualize it, it's not as complicated. So here is how it looks like so you basically take one row from this image, and so that's like a vector of numbers, and you add that to the token at that particular position. So row 0 would be added to token representations at position 0. Row 1 would go to token representations at position 1, etc. So that was the high level overview of how I think about the project when I'm developing the project. So I like to separate functionalities. I like to get end-to-end system working as soon as possible, and then I kind of go into depth. So that's the same way I learn theory. I always start high level, so first like create a skeleton and then start filling in the gaps. I pretty much do the same thing. I use the same strategy when I develop like software projects. So that was the high level overview of the project. Now I want to give you like a couple. I want to like kind of tell you about a couple of problems I struggle with. So one of them is when I was developing the transformer model itself. So it's always a good thing to kind of print out the layers you have in the model, to print out the shapes, and in general just to see how many parameters the model has. So doing that, I figured out that my multi-head attention was actually I was referencing the same object in memory in multiple encoder layers, and there was simply a bug which I discovered because I printed out these like layer names, and I saw there were some like multi-head attention layers missing. So basically, if I change this to true here, because the paper explained they had the base model and they had the big model. So if I put the big one and I run the script, I'm printing out the number of parameters, and you can see here like 176 million parameters. And that's also a good thing to do because I knew that the big model had 175 million parameters. So this kind of confirmed that that I have the same number of parameters as the paper stated. So those are just some of the things you want to do because you want to make sure that something is correct. Like it's a kind of a test, pretty much. Yeah. So the second fun experience I had was during when I was developing beam search functionality, and I actually still haven't finished it yet. I have really tested, but Beam is still not working. And while I was kind of investigating how other people did it, I found like in Tensor to Tensor library, I found like a line like this, like length penalty equals TF power 5 plus something divided by 6 power to the alpha raised to the alpha power. And I was like, what the f-? So the thing is, I beg you, if you ever write code in a public open source library, please leave a comment. It will make like life so much easier. So I don't know how, but I like kind of went through the code and some other people's codes like OpenNMT, etc. And I figured out there is a paper which introduced this esoteric heuristic, and it kind of just works. I mean, and you can see it here, 5 plus blah blah raised to the power of alpha. And I was like, what the fuck? So those are just, I just wanted to give you a glimpse of things you encounter while you're working on these projects. So it's super interesting, super funny stuff you can see. Okay, this video is getting already a bit too long. Let me just show you one more interesting problem I stumbled upon while working on the Transformer project. So it has to do with torch text and loading data. And basically you have this class in torch text which is called bucket iterator, and it's something similar to data loader if you're familiar with computer vision, like torch vision library. And what happened basically is that let me see if I can find the so what happened here is that like the documentation said something totally different from the results I was getting. So basically what the bucket iterator said is minimizes amount of padding needed while producing freshly shuffled batches for each new epoch. And that's not true. Like I had to dig so deep into the source code, and finally I submitted like I saw there is already some issue pending, and I just commented and like kind of said, yeah, that guy had right, he stumbled upon the same bug as I did. And basically you have to set this sort within batch to true, otherwise you won't get like padding minimized. And once you do that, everything. So then you get the functionality you actually wanted. And then there was a second thing. So what I wanted to do is because certain sentences are much longer than other. So if you just set the batch number as a fixed number, so for example, always load 8 sentences. Sometimes the batch will be huge. Sometimes it will be really like small, and that's a bad thing because you wanna maximize the amount of VRAM on your GPU that you're using. So what I had to do is I had to write down this custom function which will basically make sure that I always have like approximately the same number of tokens in a batch. And the annotated transformer luckily had something similar implemented, although they didn't comment why this was like why this was there. And so I struggled a lot until I actually understood the source code, and then I figured everything made sense. So now hopefully if you go through my code, it'll be a bit easier to understand what happened here. Just one more quick thing, that's that I had to add this basically custom dataset because using spaCy tokenizers at the moment, it took me 66 seconds, 70 seconds, whatever, to retokenize the source and target sentences every single time. And so I just decided, why not tokenize it once, save it as a like simple TXT file, and then instead of retokenizing things again, just load the TXT file, and that now takes like 2.5 seconds. So in a nutshell, that's what I did with these dataset wrapper and this fast translation dataset wrapper class. So that was a short story about like some problems I encountered. Now, like for the end, let me just show you how the thing functions and how the translation script actually works. And I think it's really interesting and magical for me, because I was usually doing computer vision things, and then once you see this thing actually working and translating from English to German and vice versa, it's pretty fascinating if you ask me. So I've got so you basically just have to input the sentence depending. So I have an English sentence, how are you doing today, whatever, set as a source sentence, and we have the model that was trained on IWSLT dataset, and it's translating from English to German, so the name is pretty indicative of what the model is doing and where the model was trained on. So you just have to keep these two in sync with the model. So if you change the model to G2E, German to English, you would just have to set the enum here to G2E instead of E to G. That's it. Once I start this thing, let me run it. It takes a little bit of time, 2.5 seconds to load the vocabularies and to load vocabulary, and then it'll just translate. Why is it not working? Okay, here it is. It took 2.6 seconds to load the data, and then you can see the input sentence, the source sentence tokenized, and you see the output sentence, "Wie geht es Ihnen heute?" which means the same thing pretty much. Although Ihnen is a German word, like a polite way to say you. So there's nothing stopping me from translating from German to English. Let me just change this thing to German to English. Let me change the model to German to English. And now if I input, for example, "Wie geht es dir?" which translates as, yeah, how are you, basically in English. Let me see what the model will say, how the model would translate this time. And it basically translated this as "how are you," which is pretty much something called gold translation, which means like ground truth translation. This looks pretty decent. The model is not perfect. You can find some sentences which would kind of confuse the model. So even a simple sentence like "Ich bin ein Berliner," which is a sentence like I think Kennedy said when he was back in Berlin, back in the days, and it means I'm a Berliner. I'm a person living in Berlin. And if I input this and run it, so the model will actually. The thing is, the model doesn't have a token Berliner inside the vocabulary, so that's why it will say Berlin instead of say. I'm anthropomorphizing the model here. So it will output Berlin. So I'm a Berlin. So if the model had Berliner, it would output Berliner. So that's another point I want to make here. So if I had something called byte pair encoding, the model would be much more expressive in creating these words than at this point of time. But that's a future work, and I'll add it hopefully like maybe next week or something. So there are many other things I could show you, but for the sake of this video not being like 1 hour long, let me just show you how the perf, what amount of hardware requirements do you need in order to run translations. Not in order to train the model. You would need a lot of GPUs to train the model. I actually have some comments in the README. Please go ahead and read that part. But for translations, let me just open the task manager. And if I open it up, if I run the script now, we can follow how much GPU is needed to get the translation. So it's basically only a small spike. So you won't need as much hardware like a really fancy GPU if you're just running translations. On the other side, if you're training this model, you'll need a lot of power. So that pretty much wraps it up. Hope you liked this video. There was a lot of information in here. So what my next steps will be is I'll start reading research papers again. I want to explore what's state of the art in natural language processing now in 2020. So I'll be spending like maybe reading one paper in the morning, one paper in the evening. That amounts to maybe at least 10 papers a week, which is good enough to get me like familiar with the field in like a 10 days period, 2 weeks. So yeah, that was pretty much it. If you like this video, go ahead and subscribe to this channel and hit that bell icon to get notified when I upload a new video. And until next time, keep learning.